Hello, everybody. Welcome back to another Strengths Materials video. This one is on allowable stress, flexural stress, and all of those fun concepts that we've been talking about previously. And I wanted to make another video because this concept is so important to structural engineers. It is such a fundamental principle in order to design beams and understand how stress is being distributed throughout structural elements. And I wanted to use an example in real life just to kind of highlight things that are important before hopping into this problem. So recently I was looking at this bridge that has girders spanning from one end to the other. And you're going to notice that there's two different types or two different looking girders in this problem. We have one on the left that has some levels of corrosion buildup, and one on the right that looks relatively good condition. And I want to highlight this one on the left here, which is going through that rusting. And the chemical process for rust, what it does is it eats away at the original steel and builds up this flaky debris that is no longer contributing to the flexural strength of the member. Why is this important? This is important because our flexural strength formula, or flexural stress, sorry, is governed by this I value on the bottom, that moment of inertia. And moment of inertia is controlled by your total area of your steel element. So if you're losing area in the process of rusting, then you're going to be reducing your total inertia, which means you're going to be developing a higher flexural stress in your member. And once again, if you exceed that allowable flexural stress in your member, you are failing. In simple terms, you're going to fail the member. So what we do sometimes is if this corrosion is super bad, we can do something like this where we add steel plates in sections where we are losing area and supplementing that area with a new steel member in order to bring up that moment of inertia value based on an increase in area. And we know that the further away the area is from that central axis, we are going to be greatly increasing the moment of inertia. But for now, let's just think about this problem and then see what we're dealing with. We have two beams that are being considered, and it wants us to analyze the beam that has a 150 kilonewton moment applied to it and see which is going to develop the lower bending stress. And we know in order to do this, we first need to solve for that global inertia value and then use that value to derive the flexural stress that's developed. So let's start by doing a little bit of a breakdown of what the individual components are for this composite shape. And then we can use the parallel axis theorem to solve for that moment of inertia for both of these. Okay, so now I have a breakdown of the different components, different centroids for each of the individual shapes for our composites. And we can now start using the parallel axis theorem. And the first thing that we can do is start breaking down what the areas are for our individual elements. So I numbered them section 1 or element 1 and element 2. Both the top and bottom flanges in this case are equal, so we can solve them both at the same time. So let's look at area 1. Area 1, we are dealing with a 30 millimeter thickness for that web. So we're going to have 30 times the height, which is 300. And that's going to give you a value of 9,000 millimeters squared. Proceeding to the second member or section, we have the top and bottom flanges, which are 15 mil thick and 200 mil in width. So we have 15 times 200, and that's going to give you 3,000 millimeters squared. We can do the exact same thing for the second section here as well. Alrighty, so that's the first part of the parallel axis theorem. The next thing we need to do is figure out these d values as in the distance away from our respective global axis. So our global axis is going to be placed arbitrarily at the center of our section to keep things simple. It can be at the bottom, it can be at the top, wherever you like to place it as long as you're consistent. But the reason that I place it at the center here, that x global coordinate is right at the center, because we are going to be having a zero distance away from the local and global axis of this central shape here in the center. So D1 is is going to be 0. That's going to be the case for both of these members here. And then similarly, we do the same kind of process for the second part of our member, except now we have to take a jump of half of this 300 and half of this 15 here. So we have 300 over 2 plus 15 over 2. And that's going to give you 157.5 millimeters. And we do a similar thing for the other side. Alrighty, so now we have all our variables solved for. I've just cleaned it up a little bit. Now we can go ahead and finally start plugging in for that global inertia value. And we'll start with this first member here. We know that Ix is going to be equal to Ix prime. And this first shape that we're dealing with is rectangular. So we're gonna use that typical formula, 1 over 12 base times height to the power of 3. So this is 30 mil here. And the height is 300. That's going to be to the power of 3. And the second part of this formula, the AD squared, is going to be 0 because we know that D1 is equal to 0 based on where we place that x-axis. Then we add the second part of our formula, which is going to be for the top and bottom flanges. So we're going to start by multiplying this all by 2 because we have 2 of these, okay? Same thing, start with 1 over 12 for this x prime value, that local moment of inertia, except now our base is 200 and our height is going to be 15, and that's the power of 3. Then we're also adding this second component of the AD squared. The area we solve for is 3,000, that's millimeters squared, and the D is going to be 300 over 2 plus 15 over 2, which we solved for already, 157.5, and that is squared. Close the bracket. Ix is going to be equal to, where's the number? Just looking for it, 216.5 times 10 to the 6 millimeters to 4. And we do the exact same thing for the other side of this problem as well. And your solved inertia value for the second member is 361.4 times 10 to the 6 millimeters to the power of 4. And now we can go ahead and finally start plugging in to our flexural formula to see the stresses developed in each member. So let's start with this first member here. Just going to call this member A, member B, so we don't get confused. Member A, the stress is going to equal to 150. That's the moment that's being applied, times 10 to the 6 for Newton millimeter. We have the y value, which is the distance from our centroidal or neutral axis to the top or bottom flange, as the maximum fiber for tensile stress or compressive stress. So that distance is going to be 300 over 2 plus 30 for this first member or this second member here. And then similarly, we have 300 over 2 plus 15 for this other member. So we're starting with this one here. We have 300 over 2 plus 15, and that's millimeters. This is all going to be over that inertia value that we already solved for. So 216.5 times 10 to the 6 millimeters to 4. And solving that, you're left with a value of 114.3 MPa. And we do the exact same thing for the second section here, just switching around this number. This 15 is going to be turned into a 30, and we are going to be using that other inertia value that we solved for that section. And solving for that, you will be left with a flexural stress of 74.7 MPa, meaning that section 2 or section B is going to develop a lower bending stress than section A. And that's it for the problem. Hope you guys liked seeing this picture of the real life example, and I hope it helped to understand the formula a little bit better. So, yeah, thanks for watching.